Hi everybody, this video is going to cover the oxidation states section of AQA 1.7 oxidation, reduction and redox equations. The video will cover simple charges, assigning charges, also called oxidation states, using oxidation states, and disproportionation reactions. We'll start by having a look at the reaction we looked at in a previous video. Iron oxide reacting with carbon to form carbon dioxide and iron. And I want you to have a think, what would the half equation for iron, Fe, be in this reaction? Well, to work this out, we've got to think, what will the charge on iron be? Iron's a transition metal and it can have varying charges. In this reaction, we have FeO, and because oxygen forms a 2- ion, because it's in group 6 and needs to gain 2 electrons to form the oxide ion, which would look like that, this must be Fe2 plus in this iron oxide, because the Fe2 plus and the O2 minus would make FeO. The charges would cancel, which means that our iron half equation would be Fe2 plus forming Fe, and we put 2 electrons in the centre just here, and that would be the half equation present in the full balanced equation. But what about the half equation for carbon? Now, carbon to carbon dioxide is a bit more tricky because carbon dioxide is not ionic. It's a covalent molecule, so it doesn't form ions. But we know that this is an oxidation because carbon is forming carbon dioxide. It's gaining oxygen. And we know that oxidation can be expressed in terms of electrons. Now, although carbon dioxide is covalent and not ionic, we can still work out a half equation for this process. And this is where oxidation states come in. So for many atoms, it's really obvious what the charge on an ion will be. For example, groups 1, 2, 6 and 7 of the periodic table. And if we take lithium as an example, as we just discussed with oxygen, we can talk about outer shell electrons. Lithium is in group 1, so it has 1 electron in its outer shell. In order to form a stable ion, it needs to lose that electron. So it forms a lithium ion with the outer shell now being empty, or the next shell down being the full outer shell, and this forming a +1 ion with an electron. So we know that lithium forms the Li+ ion. It is a simple ion, and the same ions would form +1 for anything in group 1, and we'd have +2 ions for group 2, -2 in group 6, -1 in group 7. They are known as simple ions, always going to be the case. But some elements have different common ions. We've already mentioned these. So for example, the transition metals. Iron, as an example, has 2 common ions. It can form Fe2 plus, as we saw previously, but it can also form Fe3 plus. So how do we know which ion we're dealing with? Additionally, in other situations, such as the carbon to carbon dioxide half equation we just talked about, we might need or want to describe redox in terms of electrons, but for non-ionic species, such as carbon dioxide. Now for these situations, we can assign charges, and these are known as oxidation states. So looking back at our equation, we said previously that oxygen forms the O2- ion. Taking that into account, if the oxygens present in CO2 were ions, what would the charge on the carbon be? First of all, we have to look at the charge on CO2. Now CO2 is actually neutral. It has no charge. And what that tells us is that the charges on the carbons and the oxygens must add together to be 0 overall. Now if we have 2 lots of O2-, that means that we have 2 lots of the -2 charge. And that tells us that oxygen contributes a -4 charge to this compound overall. Now if carbon plus oxygen cancel their charges out, and the oxygens contribute a -4, the carbon must therefore be a +4 charge. Now, as I said, we know that carbon dioxide is not ionic. So what we're doing here is we're just assigning charges and saying, if it was ionic, what would the charges be? And we can then say that the half equation for carbon would be carbon forming carbon 4+, and it must be +4e- on the right hand side. Now, although carbon dioxide is covalent, in the molecule there will be an uneven distribution of electron density. And this use of oxidation states gives us an idea of the spread of electrons in the molecule. Now, you could go back and you could remind yourself of things like polar bonding, electronegativity, to give you an idea of what we're talking about there. We don't have ions, we do have a covalent molecule, but we do have an uneven share of electrons. And this oxidation state of +4 is just us saying, if it was ionic, what would the charge be in terms of share of electrons? So there are some rules for assigning oxidation states, and it's really important that you learn these. First rule is that elements are always 0. Anything that's present in its elemental form, for example F2 or C or Xe, anything present will always be 0 if it's an element. We can see here that F2 is neutral, there's no charge on it, so the fact that there's two F's joined together, both of them adding together to be 0, they're both the same, they both need to be 0. Second rule is that the transition metal oxidation states are given by a Roman numeral in the name of the compound. So iron 2 sulfate here tells us that it's Fe2+ and SO42- together in that compound. The third rule is that group 1 metals are always +1. There aren't any exceptions. If it's a group 1 metal present in a compound, the charge on the ion will be +1. The same goes for group 2. Group 2 always form +2 ions in any compound. And aluminium always forms +3. So there aren't any exceptions, always those charges, and that's when they're present in compounds. Rule number 6 is that fluorine is always -1. And if you think about what we know about fluorine, fluorine is the most electronegative element. That's the reason why this one has no exceptions and always forms a -1 ion if it's in a compound. Rule number 7 is that oxygen is normally -2, but we do have a couple of exceptions. If oxygen is present in a peroxide, for example hydrogen peroxide, H2O2, which has the structure shown on screen, then oxygen won't be -2. And also, if oxygen is in a compound with fluorine, it won't be -2 either. Rule number 8 is that chlorine is -1, except when joined to fluorine or oxygen, when it will be positive. And that's because F and O are both more electronegative than chlorine. But normally chlorine is -1. And rule number 9 is that hydrogen is +1, except when it's in a metal hydride, when it will be -1. Now, metal hydrides are where metal and hydrogen join together and form a compound. Now, if something is not mentioned on the rules for assigning oxidation states, then all other oxidation states or assigned charges must be deduced. So if it's not listed on this set of rules, you have to work out what the charge would be. So we're going to go through some examples. We're going to start with O2. The most important thing to realise is that when you're working out oxidation states, you have to refer to the rules. So I've put them on screen. Now, obviously in an exam you won't have them to refer to. You must make sure that you learn these. Now you have to work your way through the list, looking at the elements present in your compound, ion or species, and you have to find the element on the list and apply the rule. Now if the element is not on the list, it means that you have to deduce the oxidation state from the other elements present. Now O2, as our example, this is an elemental form of oxygen. It's an element. Now, rule number 1 tells us that elements are always 0. So that means that the oxidation state or oxidation number of oxygen in O2 equals 0. Our second example is one we've already looked at, CO2. Now this is a compound and it's neutral. And that means that the charge on the carbon plus the charge on the two O's must equal 0. So we look down the list first of all. Can we find carbon? Carbon isn't on the list, so we put that aside for the moment. Is oxygen on the list? We can see that oxygen is rule number 7. Oxygen is -2, except in peroxides and compounds with F. Well, first of all, we can see that there's no F in CO2. And second of all, this is not a peroxide. This is a dioxide. So that part of the rule, those two parts of the rule, for oxygen, rule number 7, don't apply to oxygen, which means that O has to be -2 in this compound. So taking our C plus 2O equals 0 rule, we can work out what C must be. Carbon has got to be 0 minus the 2 lots of the oxygen's charge, which is -2. Each oxygen has a charge of -2. So carbon is equal to 0 minus -4, carbon's +4. And those are the oxidation states of the two elements in carbon dioxide. You can write +4 or 4+, either way round it doesn't matter. Our next example is the carbonate ion. Now this is a compound ion. That means that it is a group of atoms joined together that have a charge. And its overall charge is -2. Now that means that carbon plus 3 lots of oxygen have to equal -2 overall. As we just saw, carbon doesn't have a rule, but oxygen does. Now again, there's no F in this compound ion, so that part of the rule doesn't apply. And this is not a peroxide, it's a carbonate. So that part of the rule doesn't apply either. And that tells us that oxygen's charge, again, is -2 or 2-. Taking our little equation into account, the carbon has therefore got to be the -2 overall minus the 3 lots of oxygen, which we've just said is -2. So carbon's overall charge is -2 minus -6, -2 plus 6, and therefore carbon's oxidation state is again +4. And those are the oxidation states of C and O in CO3 2-. Our final example is C2O4 2-. There's no rule for carbon, and there's no F, and this is also not a peroxide. You will always be told if it's a peroxide, it had peroxide in the name. So again, we can work out that oxygen has to be -2. Now looking at this in a little bit of algebra again, 2 carbons plus 4 oxygens has to equal -2. So carbon is going to be -2 minus the 4 oxygens divided by 2. -2 minus 4 times -2 divided by 2. -2 plus 8 divided by 2. So that would be 6 divided by 2. -2 plus 8 is +6. And that tells us that in this ion, carbon has an oxidation state of +3. Now we've been through some examples, it's your turn. Activity 1. Give the oxidation states for each element in the species given below. Make sure that you refer to the rules. This isn't a test. Have those rules in front of you and use them as you practice. There's 10 to have a go at. Work out the element oxidation state for each one. Pause the video and the answers will follow. So on to the answers. First of all, CCl4. It's a compound, so it's neutral overall. There's no rule for carbon, but there is a rule for chlorine. Chlorine is -1 unless it's joined to O or F, which it's not in this case. So Cl is -1. There are 4 lots of -1, which means that there is a -4 charge overall from the chlorines. And for the compound to be neutral overall, carbon has to be +4. For PbCl2, again the rule for chlorine is that it's -1 unless it's joined to F or O, which it isn't in this case. So chlorine is -1. Now there are 2 lots of chlorine, so 2 -1s, so chlorine is contributing a -2 charge to the compound. There isn't a charge overall, so for the compound to be 0, the lead has to be 2+ to cancel out the 2 negative chlorines. This would be lead 2 chloride. That's where we get the names from, because its oxidation state for lead is 2. For number 3, Br2, bromine's an element in this particular question, and therefore bromine's oxidation state is 0. For PF5, we need to think about our rules. There's no rule for phosphorus, but there is a rule for fluorine, and fluorine is always -1, absolutely no exceptions. There are 5 fluorines in this compound, so 5 times -1, fluorine contributes a -5 charge overall, and therefore phosphorus must be +5 for the 5 negative fluorines to be cancelled out and be a 0 compound overall. For Fe2O3, there is no rule for iron, but there is a rule for oxygen. This is iron oxide, it's not a peroxide, and there's no fluorine, so the oxygen has to be -2 according to our rules. Now the oxygens, there are 3 of them, so the oxygen contributes a -6 overall to this compound, which means that the ions have to contribute a +6 overall. But there are 2 ions, so that +6 charge, is divided over the 2 ions. So iron has a charge here, its oxidation state is +3. That means that this is iron 3 oxide, because the oxidation state of iron is 3. On to the ions. PO43- is the phosphate ion. Overall, we've got a 3- charge, which means that the P's and all 4 O's have to add up to -3 overall. Now oxygen is -2 because it's not a peroxide and it's not got any F's. There are 4 oxygens, so oxygen overall will contribute a -8 charge to this compound, which means that the phosphorus has to be +5, because +5 for the phosphorus minus the 8 for the oxygens present equals -3, and that is the overall charge that we have here. For the nitrate ion, again oxygen is going to be -2. There's no fluorine and it's not a peroxide. There are 3 lots of -2, so oxygen is contributing a -6 charge overall. For the overall charge to be -1, nitrogen has to be +5. Because the +5 from the nitrogen minus the 6 from the 3 oxygens, that will equal -1, and that's what we said our charge was. For the ammonium ion, again no rule for nitrogen, but we do have a rule for hydrogen. Hydrogen is +1 unless in a metal hydride. This is not a metal hydride, there's no metal, and therefore hydrogen is +1 in this example. There are 4 hydrogens, so 4 lots of +1 is +4. This means that the nitrogen has to be a -3 for its oxidation state, because -3 for N plus the 4 hydrogens overall equals +1, which is what the overall charge in this compound ion is. For HSO3 we now have 3 elements, but we still use the same rules. Hydrogen is always +1 unless it's in a metal hydride, which this isn't, so hydrogen is +1. Sulfur we don't have a rule for, so we need to leave that for now. But oxygen we know will be -2 because it's not a peroxide and there's no fluorine. Now the oxygen, there are 3 of them, so oxygen contributes a -6 charge overall. So sulfur plus hydrogen plus 3 lots of oxygen will be -1. We've just said that the hydrogen is +1, so I've put this on the right hand side to make it -1. The oxygens contribute a -6, so if I move those to the right hand side, that makes it +6. -1 minus 1 plus 6 equals 4. So therefore sulfur's oxidation state is +4 in this ion. And finally dichromate, Cr2O72-. Now again the oxygen is going to be -2 because there's no F and it's not a peroxide. We have 7 of these oxygens, so overall the oxygen will contribute a -14 charge overall. Now if the overall charge on the ion is -2 and the oxygen is -14, we must have a +12 from the chromium to make this mathematically correct. So 12 over 2 will be what chromium is on its own, because we have 2 chromiums just here. So the chromium oxidation state will be +6 in this particular example. Now that we have an understanding of how to calculate oxidation states, we can use oxidation states to work out whether a reaction is redox or not. We're going to use the example copper sulfate plus zinc forming copper and zinc sulfate. If we work out the oxidation state of each element before and after the reaction, we can see how the oxidation states change, and that will tell us whether the element has been oxidised or reduced. Now, zinc is an element, which means that its oxidation state is 0 at the beginning of the reaction. Oxygen is not joined to F and is not part of a peroxide, so oxygen will be -2. Copper has to be +2. Sulfate is SO42-, that's one of the ions that we need to learn, so the copper therefore has to be the copper 2+ ion for CuSO4 to be neutral overall. Sulfur is +6. Now we can work that out using the rules. There are 4 -2 oxygens, so -8 overall for oxygen in the sulfate ion, so sulfur has to be +6 for the +6 and the -8 to equal the -2 charge of the sulfate. After the reaction has occurred, copper is now an element, and that means that the copper's oxidation state is 0. Sulfur is still part of the sulfate ion, SO42-, so the sulfur hasn't actually changed, and the sulfur will be +6 after the reaction as well. Oxygen is also present in the sulfate ion and hasn't actually chemically changed. The zinc is now part of zinc sulfate, and therefore zinc has to be zinc 2+ for the compound to be neutral overall. The sulfur and oxygen are part of the sulfate ion, and therefore they are actually spectator ions. The sulfate itself is the spectator ion, SO42-. It's chemically unchanged, and we can see that from the oxidation states. Now if we look, we can see that the copper has gone from +2 to 0. Its oxidation state has gone down. And using oxidation states, the oxidation state has reduced, gone down. Therefore the copper has been reduced. Now we can double check that with electrons. Cu2+ would have to gain 2 electrons to become Cu0. And we know a gain of electrons is reduction, and therefore that must be correct. The zinc has been oxidised. The zinc has had an increase in oxidation state from 0 to +2. Now because we have one substance that's had its oxidation state going down and one with its oxidation state going up, that tells us that this is a redox reaction. One substance has reduced and one substance has oxidised. And we can apply a little rule for this. A reduction in oxidation state means that we have a reduction reaction. Our second example is the reaction of chlorine with water. we're going to do the same thing again and look at the elements and how their oxidation states have changed. Chlorine is an element on the left-hand side, and therefore its oxidation state is 0. Hydrogen is present in water, therefore it will have an oxidation state of +1. And the oxygen is not in hydrogen peroxide or bonded to an F, so oxygen will have an oxidation state of -2. On the right-hand side of the reaction, we can see that oxygen is still not bonded to F and not part of a peroxide, so oxygen will be a -2. The hydrogen is present in 2 different species, but in neither of them is it bonded to a metal. So in hydrogen chloride, hydrogen is +1, and in the hydrogen chlorate, it's also +1. In hydrogen chloride, the chlorine must be -1. We can work that out because the hydrogen is +1, but also because we know the rule for chlorine, that chlorine is always -1 unless bonded to O or F, which it isn't in this case. In HOCl though, if the hydrogen is +1 and the oxygen is -2, that tells us that the chlorine has to be +1 for there to be a 0 charge overall. And what we can see here is that the chlorine has gone from 0 to -1 and from 0 to +1. Its oxidation state has reduced and increased. Now the reduction in oxidation state is a reduction, and an increase must be oxidation. This reaction is an example of a disproportionation reaction, where the same element undergoes both oxidation and reduction. It's still a redox reaction because we have reduction and oxidation happening at the same time, but the share of electrons is being shared disproportionately, unevenly. Disproportionation reactions are still a type of redox reaction. So activity 2. For each of the following reactions, I'd like you to give the oxidation states of each element both before and after the reaction. State whether the reaction is redox, and if it is it disproportionation? And for C, identify the species that have been oxidised and reduced, the oxidising agent and the reducing agent. There's 3 reactions for you to have a go at, and make sure you show your working. Okay, so answers for activity 2. Question number 1 is the reaction of magnesium and hydrochloric acid. So we have magnesium, hydrogen and chlorine. On the left hand side, magnesium is 0, and on the right hand side it's +2, Cl must be -1, and there's 2 of them. The hydrogen is +1 on the left hand side and 0 on the right because it's an element, and the chlorine is -1 on the left hand side and -1 on the right. We can see that the hydrogen is reduced because its oxidation state has gone down, and the magnesium's oxidation state is increased, so that is the oxidation. Therefore it is redox, but it's not disproportionation because we have 2 different substances that are being oxidised and reduced. The magnesium is being oxidised and therefore must be the reducing agent, and the hydrogen is being reduced and is therefore the oxidising agent. Question 2, we have hydrochloric acid and sodium hydroxide. So HCl, Na, O. Hydrogen is +1 in the HCl, it's +1 in the sodium hydroxide, and it's +1 in water, so that does not change. The chlorine is -1 in HCl and -1 in NaCl. The Na is group 1, so that is always +1 on both sides. and the oxygen is not bonded to F and not in a peroxide on either side, so is -2. There's no change in oxidation states, therefore it's not redox. If it's not redox, it can't be disproportionation, and we don't need to worry about identifying oxidation agents or reducing agents because it's not redox. Question 3, we have the decomposition of hydrogen peroxide. So we just have H's and O's. The hydrogen is +1 on the left because it's not in a metal hydride, and is also a +1 on the right because it's still not a metal hydride. The oxygen starts as -1, and that's because we have hydrogen peroxide. If hydrogen is +1, each of the oxygens have to be -1 for its overall be 0. In water, the oxygen is -2 because it's not a peroxide and it's not bonded to F. And we also have oxygen present as an element, so it's a 0. So we can see the oxygen is going from -1 to -2, but it's also going from -1 to 0. We have a reduction in oxidation state, so therefore a reduction reaction, but the oxygen is also being oxidized as it has an increase in oxidation state. So therefore it is redox, and because the reduction and oxidation are both happening to oxygen, it is also disproportionation. And this shows that hydrogen peroxide can act as both a reducing and an oxidizing agent.